Good morning, everybody, and welcome to CNS 2021. I apologize for the slight delay for our first session. We have our first keynote speaker, Dr. Wolf Singer, who was trained as a physician in Munich, did a dissertation in Munich, and is now at the Brain Institute at the Max Planck in Frankfurt. Dr. Singer is one of my heroes because based on theoretical findings and ideas, he pushed ideas that were not always popular at the time. And he's the founder of ideas about synchrony and binding and segmentation and cognition in the visual system. And without further ado, here's Wolf Singer.
Thank you, Christiane, for this introduction. Apologies for being late, but we had communication problems as usual. Good morning to you in the States, and good afternoon for those in Europe here. If one compares those two information processing systems, it at least suggests a little bit that nature and evolution may have found complementary strategies to the strategies applied in these supercomputers. The deep learning networks that are so popular nowadays because of their superior performance, they essentially are feed-forward processing devices where an input vector, some feature constellations are forming conjunction-specific units in hidden layers by divergence and convergence of offering upstream connections, and then there are classifier output units at the end. These deep learning networks encode relations essentially by conjunction-specific units, and we call this a labeled line code. But the limitations of this strategy are that there's a combinatorial explosion if all possible relations should be encoded in individual labeled line nodes, so it's very hard, very expensive. Then there is a difficulty to encode temporal relations for the simple reason that these feed-forward networks are clocked and they don't really use time as a coding dimension. Then they have little generative capacity because they are trained on massive data sets, and essentially it's a match of input to output that is achieved by learning algorithms. Now, these limitations can to some extent be complemented by dynamic encoding of relations, and we address this as assembly coding. That means units representing components are transiently bound into coherent assemblies that are distinguished by correlated activity. So in this case, nodes that code for particular features, that are selected for particular features, they can be assembled in cooperating groups of cells in order to express different relations between features in a dynamic way. So this dynamic encoding, however, of relations requires reciprocal interactions among the nodes. It cannot be realized in feed-forward architectures. It requires recurrent connectivity, but this is not a problem for nature because it is a hallmark of natural systems. We find it in hippocampus, we find it in cerebral cortex, we find it in the mushroom body of insects. It's ubiquitous in living systems. Now, if one considers, for example, two cortical columns, example here in the visual cortex, tuned to particular features, orientation or color, there is some feed-forward processing from the input layer 4 to supergranular layers and then down to infragranular layers. But the large majority of the synapses formed, in particular in the supergranular layers 2 and 3, they are derived from these red lines, which are axon collaterals, so projection neurons, that interconnect reciprocally neurons, pyramidal cells in layers 2, 3 of the supergranular layers. So 80 to 90% of the synaptic contacts are actually constituted by these recurrent connections, as well as by the recurrent connections that come from higher cortical areas and are conveying top-down information. So the characteristics of recurrent cortical networks are that nodes are feature selective, and the connections have Hebbian synapses. This is a very important point. They are adaptive and they change their gain as a function of a correlation rule. Hence, nodes coding for correlated features, they get strongly coupled because if these features co-occur frequently in the environment, those nodes will be activated, co-activated, and the coupling among them will increase. So the synaptic weight distribution eventually reflects the correlation structure of the sensory environment. It harbors the priors or the internal model of the world. Now, another property of recurrent cortical networks that is very important is that all the nodes have a propensity to oscillate, either because they contain pacemaker neurons or because the microcircuitry recurrent inhibition makes them likely to oscillate if driven appropriately. This means that if co-activated, strongly coupled nodes are activated, they tend to engage in resonance and correlated firing because of this propensity to oscillate. They can resonate. So one can look at the supragranular layers. This is a top-down view on very simplified on the supragranular layers. We have nodes that are feature selective for particular orientations, color, direction, and motion, simple features of the visual world in primary visual cortex. These nodes have a propensity to oscillate, as indicated here with the sinusoidal line, and they are reciprocally coupled. And these coupling connections are anisotropic. They follow a nearest neighbor rule, but they also are strengthened selectively among nodes that in the past had a high probability of having been activated together. Now, this system is in addition influenced by top-down feedback loops that contact those nodes, and the general excitability of the system has to be regulated very carefully. It operates close to criticality, and this is a task that is achieved by internal homeostatic mechanisms as well as by ascending modulatory systems. Now, in natural systems, of course, feed-forward and recurrent processing coexist. They are combined. And the feed-forward processing essentially creates feature-selective nodes, so the labeled line code that I have mentioned before, while the recurrent processing task is the dynamic grouping of nodes. So how can those two strategies be combined? The hypothesis is that the correlation patterns that emerge in the recurrent network, they reflect the match between sensory evidence and the internal model of the brain. And these correlation patterns in turn determine the responses of the conjunction-specific units at the next level. Now let me make this a little bit clearer. Imagine a pattern at the input stage consisting of oriented lines of different orientation. But a subset of these lines, they are collinearly aligned, which immediately, according to Gestalt criteria, produces a pop-out of a collinear arrangement here. Now, all those contours are supposed to have the same contrast, same energy, and all the feed-forward connections here, the blue lines, they are supposed to have the same gain. And there are the recurrent collaterals, which are depicted here in red. Now, because elongated contours are very frequent in natural environments, the pyramidal cells 3 and 4, which get their orientation selective input from layer 4, and it's just inherited, they will have been co-activated frequently in the past because of the occurrence of elongated contours that hit their receptive fields. Hence, because of the synapses that are adaptive here, following a Hebbian correlation rule, those recurrent connections, those reciprocal couplings will become strengthened with experience. So if those two cells see something that drives them, in this case, they are tuned for horizontal orientations because the feed-forward lines from layer 4 are tuned to horizontal contours, they will engage in cooperative interactions much more than the others who have less strongly connected reciprocal pathways. And this resonant state or cooperativity will increase either the discharge rate of those two neurons, or it will make them more coherent, will synchronize them. Hence, the target cells in the next processing stage, they will receive stronger inputs because of the coincident sensitivity of cortical neurons. They will be sensitive to the higher degree of correlation arriving or in the activity that arrives from units 3 and 4, and hence they will produce stronger responses and signal to the next processing stage that these two are coding for something that is related, in this case, collinearity. So, if this is so, this makes a strong prediction. It predicts that nodes that are activated by features that match the predictions, the stored priors, they should synchronize or become more coherent and thereby signal that they encode a related set of features. And there is evidence now from experiment that stimuli that match predictions that are in this case derived from context, the embedding context, evoke resonant responses. And an example that I will show you is taken from the feature domain color, because in the cerebral cortex, color is treated as a feature, just as much as it is the case for orientation, because they're color-sensitive neurons. This is not so for brightness, as you will see in a minute. And the surprising finding is that if one presents a monochromatic surface, it needs to be colored. Two neurons in V1 in awake behaving monkey. One sees that this monochromatic surface evokes a very, very strong oscillatory response in the gamma frequency range. This is the power of the local field potentials. This is not the case if this surface is just bright. So a achromatic surface doesn't do it because it is not treated as, brightness is not treated as a feature by the cortex. So if this same monochromatic surface, and it doesn't matter which color it is, produces this strong increase in power in the oscillatory range of about 50 Hertz, which is gamma, there's also a strong spike field coupling, indicating that also the neurons, all these neurons that are activated by this monochromatic surface, they tend to engage in correlated firing, in synchronous firing. Otherwise, there would not be this consistent relation between the spiking and the occurrence of the field potential. And this is not so in case of black and white, just a white surface. In this case, there is no locking of spikes, they are not synchronized. Now, in this case, the embedding context, the color, predicts the stimulus in the receptive field, which is just the same color as the surrounding. One can now disrupt this prediction by either presenting in the center a dot of a different color, or surround the center by a ring, disrupting the continuity between the embedding surround and the center of that considered neuron. So violating the prediction that what should occur in the center is predicted by the surround. And this gives a completely different picture. If one presents now again the monochromatic surface, which is here in blue, uniform surface, and considers the discharge rate of the neurons, there is the initial transient when the stimulus comes on, but then very quickly the neurons adapt and they go beyond baseline for the rest of the time. If, however, the prediction is violated, if the center stimulus is of a different color, or if there is an annulus, there's a very, very strong rate response. So a non-predicted stimulus, a center stimulus that does not conform to the context of the environment, produces a strong rate response. If one looks at the LFP power, the reverse is the case. The uniform stimulus produces a very strong power increase. You have seen this already. But a blob stimulus that produces these strong rate responses is not increasing the LFP power, nor is it in the annulus. And the baseline just shows the normal 1/f distribution of power as a function of frequency. So these results suggest the conclusion that discharge rates and synchrony code for different aspects. It seems as if discharge rate would signal prediction error, a mismatch between sensory evidence and the predictions, in this case, the prediction provided by the embedding context, while correlated firing signaled the match between the stimulus and the environmental predictions. Now, there are computational options offered by recurrent processing that go well beyond what I have been telling in a moment. So assembly formation or grouping of responses according to relatedness, the match with stored priors. And the reason is that recurrent networks, they generate very high-dimensional nonlinear dynamics that can be exploited for computations. And some of these properties are exploited in reservoir computing or liquid state machines. The principle of reservoir computing, for those who are not familiar with it, it essentially transforms a low-dimensional input pattern into a very high-dimensional dynamic state, and then does the classification in this high-dynamical state. Imagine a pond of water, drops falling into it, or stones, creating, traveling, expanding waves. And if there's a sequence of events of throwing stones or drops, A, B, C, D, waves will propagate. There will be a very complicated interference pattern. And then one can decode the sequence of events by simply measuring at 3 or 4 points in this pond. And the pond has a memory as long as the waves are propagating and measurable. If one measures amplitude, wavelength, and frequency and phase, and then one can reconstitute, training a classifier, what the sequence has been. And because of this high-dimensional space, patterns that will overlap with low-dimensional space can be segregated through this trick, which is actually used in technology. Now, it so happens that the recurrent network actually has the properties of such a liquid. If one disturbs one of the nodes in a recurrent network, one gets traveling waves, one has fading memory because of reverberating activity. But the big difference is that the nodes in natural networks, they are feature selective. The connections are anisotropic and they are learned, they are weighted according to a Hebbian correlation rule. The fading memory is also more complex than just propagating waves in a homogeneous water. So, is there any reason to believe that this is a principle that can be applied to the analysis of cortical structures? I would suggest yes, because the dynamics of recurrent networks, they do provide such an extremely high-dimensional coding space. And this permits the storage of a vast amount of information, which is required in order to store all the priors that one needs in order to segment, for example, visual scenes. It allows for parallel search and therefore for ultra-fast readout, which is also required because we change our gaze every 200 milliseconds, roughly. So every 200 milliseconds, a different set of priors needs to be pulled out of the store and matched with the incoming sensory evidence. Then, of course, there's a good separation of representations for classification if the representation space is high-dimensional. And the fact that recurrent networks exhibit fading memory due to reverberation, they are at ease with the encoding of sequences. They can superimpose information of sequentially presented stimuli, so they can integrate over temporally disjunct information. So there are a few general predictions that one can derive from this. One is that resting activity should exhibit very high-dimensional correlation structure and reflect the priors that are stored in the weight distributions of the recurrent connections. And stimuli that match the priors, the predictions that reside in this functional architecture, they should induce low-dimensional substates, a rapid collapse of this high-dimensional spontaneous state into a low-dimensional substate that is characterized by specific correlation patterns and then can be classified. And these substates would, by definition, already be equivalent with the result of a Bayesian matching operation. So the result of comparing sensory evidence with stored priors. So for testing these predictions, and I will spend the rest of my talk on this, requires multi-site recordings from any cortical area. I take the visual cortex. And it requires to retrieve stimulus-specific information in the high-dimensional response vectors using machine learning techniques. And a couple of years ago, we started together with Wolfgang Maas and Danko Nikolic to take this hypothesis seriously, recording from 60 neurons simultaneously in primary visual cortex. In this case, it was still cats, presenting them with alphabets, letters and numbers taken from the Latin alphabet, one obtains these high-dimensional time series, so vectors of the responses of these 60 cells, and then presenting stimuli at different times sequentially, stimuli lasting 100 milliseconds, convolving these point series with a sawtooth function into a continuous function, and then train classifiers. We tried both linear and nonlinear ones to identify from a particular time or time interval of such a vector what the stimulus has been. Putting a window here, asking whether one can still identify stimulus A or C, and so forth. And there we found that we could actually, of course, after presenting the first stimulus, decode what that stimulus was well after the stimulus was finished, because this is the reverberating activity that carries on. But even if a second stimulus is shown, there is a moment in time during and after the presentation of the second stimulus here, where one can decode both the second stimulus and still the first stimulus, and one can even decode properly the sequence order, whether the first stimulus was an A or C and the second was a B or D. So this was encouraging because it told us that the information can be retrieved from multi-cell recordings, that it is distributed across many neurons. We needed about 40 to get saturation of the decoding performance, that there is the phenomenon of fading memory, that we have persistence of information across stimuli, that we have superposition of information about different stimuli, and that sequence order can still be decoded from these superimposed activity patterns. So we thought we should continue doing these investigations and derive further predictions. And the next prediction is that if stimulus-specific substates self-organize on the basis of stored priors, classifiability of these multidimensional vectors should improve with reverberation, because then the network can add its own information to the sensory evidence. And the second prediction is that if there is something like perceptual learning or updating of priors following repeated stimulation, classification for these familiar stimuli should improve. So Andrea Lazar did the following, extending these previous experiments, showing a large number of these letters in different sequences to the animal, hence primary visual cortex. Here are the classical rate responses, 100 millisecond long stimulus, strong rate increase, phasic, but then long after the stimulus is over, there is still reverberating activity. And that increases to some extent for late trials. So for familiar stimuli, once an animal has seen 400 of them, there is this increase of the tail. What is also interesting is that one classifies the rate vectors at different times here. Surprisingly, in these experiments, classification performance was not particularly good for the phasic transient, but it increased dramatically for this reverberating part. And it increased even more once the stimuli had been familiarized, those red lines. The reason why classifiability gets better as time elapses after the stimulus, during reverberation, the stimulus is here, is that in PC space, the clusters, the vectors of the three different stimuli that we try to discriminate here, they get segregated better. So the network adds its own knowledge in order to pull those representations apart, which facilitates classification. So the conclusion is the network apparently self-organizes into classifiable stimulus-specific substates, and this can do it within a few hundred milliseconds. The overlap of substates in PC space decreases with repeated stimulation, facilitating classification. So it's a sort of a non-supervised updating of priors. It also occurs in anesthesia, interestingly enough. And stimulus-specific information is contained in these self-generated correlation structures of the high-dimensional vectors. So the information is in the correlation. One cannot trial scramble those vectors because there is some internal correlation structure that is specific for a particular trial. Other prediction is if the priors acquired by perceptual learning are stored in the synaptic weight distributions of the recurrent network, then they should be also retrievable in the covariant structure of resting state activity, because resting state activity will mirror the functional architecture of the recurrent network. The correlation structure of spontaneous activity must somehow be related to the anisotropic weight distributions of the recurrent network. So Andrea went one step further, Andrea Lazar. She trained a matrix of classifiers, 12 by 12, to read the brightness values from the multi-cell vectors when a particular stimulus has been shown. And this leads to a reasonably good reconstruction of the stimulus, as you can see here. So if a stimulus F is presented, these decoded from the rate vectors, these matrix of decoders reconstructs these brightness values. It looks like an F. And then Andrea went on, after she had trained those classifiers to the letter-specific firing patterns, she made another analysis, which I'm skipping here, to identify in the train of spontaneous activity bursts that are likely to contain some replay information. They have a particular frequency spectrum, and they can be seen in the LFP. But so she identified those parts in the spontaneous activity that are suspicious, and then applied her classifiers to a short stretch of activity, and she actually found that, yeah, in spontaneous activity, there is the replay of the stimuli that the animal had been seeing very often. And sometimes there is something that could not identify, but if then a real letter is shown, the classifier, of course, finds the C. After a little bit of reverberation, it's there. So this leads to the conclusion that cortical networks store stimulus-specific information in the functional architecture of their connections, and that would suggest it's mainly the recurrent connections that do this, rather than the feed-forward connections, and that the correlation structure of resting activity does reflect these changes in weight distribution that are induced by prior experience. So it's a sort of a replay. It's also known to happen in the hippocampus. Another prediction: if the statistical relationship of natural environments are stored in the weights of the recurrent connections, then natural scenes should induce correlation patterns that contain more information than those induced by scrambled scenes, because they match better the stored priors. And that should result in enhanced classifiability. So this is what we actually see. Now this is a wake monkey presented either with natural scenes, again, primary visual cortex, or with their scrambled counterparts. Same energy. We get these multi-cell vectors and then try to classify them and find out which stimulus has been presented. And classification performance is possible for these scrambled images, but it is much better for the natural images, as you can see by the green line here. This is not due to changes in firing rate, because they are exactly the same for the two stimulus types. And it's also not due to a change in signal-to-noise ratio, because the reduction of Fano factor that one gets whenever one simulates such a network is virtually superimposed, is identical for the natural and for the scrambled stimuli, suggesting that a good match leads to correlation structures that facilitate classification. Now, there is another finding that was not predicted, but I think it is interesting in this context. It is known that spatial attention produces very little effects in primary visual cortex. There's virtually nothing happening there except for some decorrelation of responses. But we found that spatial attention increases the decodability of substates that are induced by the attended stimulus. But it does so preferentially for stimuli that match the priors. It does not make a big difference for stimuli that are scrambled, that do not correspond to the Gestalt principles of the natural environment. So here's the evidence. Animals were presented, again, awake behaving monkey, either with natural stimuli, with their face-scrambled counterparts, or with a mixture of Gabor patches. The paradigm was that monkey was fixating, and he received two stimuli, one on each hemifield, whereby one of the stimuli was on the receptive fields that we had been recording from. Here's the fixation point. And then the fixation point changed its color. When it was red, it told the monkey, pay attention to the right stimulus, and if it changes, press the lever or relieve the lever. And ignore a change on the other stimulus. So attention was directed to the stimulus on the receptive fields, which we call the attention in condition. Or a blue fixation point told the monkey, attend to the other side and respond if something happens here, and don't respond if this stimulus changes. So it's an attention in, attention out task, very classical. What we saw is, again, if one looks for the information content, i.e. the classifiability of the vectors that one obtains, that one gets more information out of these vectors for natural stimuli, and it doesn't really matter whether attention is in or out, these two green lines. Then one gets for the Gabor patches, or one gets for the scrambled. Natural is always better. But what is really interesting here is that when the attention cue is put on, and the monkey is, from this moment on, the monkey knows which stimulus to attend, the decodability for natural stimuli does not decay as much as for unnatural stimuli, for the Gabors or for the scrambled stimuli, but it declines less, so decodability is better here to the attended stimulus in both cases as it is to the non-interpretable stimuli, if you like. And the reason why this decodability of the attended stimulus is better is that in PC space, stimuli that are attended to tend to evoke vectors that cluster in different corners of PC space, they are more segregated than the same stimuli if they are not attended to. And the rate differences are virtually zero. Whether attention is in or whether attention is out, it doesn't influence the rates at all. So attention does something interesting. It changes the segregation of the stimulus representations in high D space without altering too much discharge rate, or not at all. And it does so mainly for stimuli that match stored priors. So the summary is, of this part, classification of scenes is possible, both from spike and LFP vectors. I didn't show you those. This is mainly the power of oscillations in particular frequency bands. Classification is always better for natural than scrambled scenes. It's not caused by differences in signal-to-noise ratio. Natural scenes induce stronger coherence. And the proposal is that the match between natural scenes and stored priors leads to well-organized substates that are reflected by increased coherence and better classification. Now, another interesting prediction that one can derive from recurrent networks is that they should exhibit sequential activation of their nodes. If one disturbs such a network, it always produces sequences. Some people also call them songs. And these sequences should somehow be related or reflect the match between sensory evidence and the stored priors. They should be influenced by both variables. Hence, these sequences ought to be stimulus specific. And this, I think, was an a priori prediction. Their precision increases with the quality of the match. So what Jan Yieling did was a very original approach. In all visual experiments, usually, and this is again a awake behaving monkey trying to fixate, if one switches on a stimulus, they are usually square waves. They are instantaneously switched on and off. So, and if you do this, you get transient responses across all the neurons, in this case, 60 channels. Recordings from V4 and also from V1, which I won't show. Now, he had the idea to expand this initial transient by ramping up the stimuli slowly. And this showed very clearly that the different nodes, i.e. neurons, respond at different times. And one can then rank order them, and then one gets this nice rank order of responses. And it turns out that this rank order is stimulus specific. If one makes the rank order of onset latencies or peak latencies, it gives the same result. For one stimulus, it does not apply to another stimulus and not apply to the third stimulus. These were natural scenes again, suggesting that these sequence orders are stimulus specific. And it actually turns out if Yieling uses classifiers that only look for rank order and not for absolute latency and not for relative latency, but just for rank order, because the time frame of these sequences changes, of course, from ramp to sudden onset. They get compressed by sudden onset. So rank order stays the same, but the temporal spacing of the song changes. And it turns out that just using rank order for classification, stimuli can be very well decoded in the no ramp condition, when all the transients are seemingly at the same time, but they are still staggered. It's best for fast ramp, but it's also nice for slow ramp, and it works for different intensities, i.e. for very different latencies and different delays among the sequential activation of the nodes. This allows, if one classifies stimuli according to sequence, to rank order of sequential activation, a much faster classification. Because one can take, Yieling tried this here, how many of the fastest responding nodes do I have to take until I get a reasonable decoding of stimulus identity for natural images? It's about less than 10. And they respond within the first 100 milliseconds. So within 100 milliseconds, one can read out what the stimulus was. If one did the same with discharge rates and used the same integration windows, performance is very, very bad. So using this temporal code would allow one to read out the grouping operations from the recurrent network in V1, it works as well, and in V4, with a very short intervals, right at the onset of the responses. And interestingly, this classification also depends again, if one uses rank order, on the nature of the stimuli. It's best for natural stimuli that probably correspond best to the stored priors. It's less good for morphed stimuli, where some of the higher order statistics have been removed, and it is worse for the scrambled stimuli. And again, this is not a rates question, because we are looking only at the rank order of sequential activation of the nodes. So, conclusion from this sort of experiments is that network interactions, they generate stimulus-specific response sequences. The consistency and hence the decodability of the sequences is best for natural stimuli that match the internal model. And the encoding information in sequence order allows for ultra-fast readout. But one then has to rely on this temporal code rather than on the rate code. And Yieling has simulated recurrent networks endowed with Hebbian synapses. If we have time, we can look at these data in the discussion. And they more or less reproduce nicely the results he has obtained here. So let me come to the general conclusions. The dynamics of recurrent networks allow for very powerful computations. And this is probably the reason for the evolutionary success of these recurrent networks that are not only found in higher mammals that possess a cerebral cortex or hippocampus, they are apparently ubiquitous also in the insect world. There they solve the problem sometimes with pure analog computations, since in these small brains you don't have to have spikes in order to communicate between neurons. Now, next step forward would be one has to investigate with massive parallel recordings, many more nodes. And what I'm looking for, because I am just trained as an MD, mathematical techniques for the analysis of these extremely high-dimensional, non-stationary activity vectors that give no information whatsoever if one looks at them with the naked eye. One cannot average. Histograms are of no use because much of the information is in the correlation structure of these single trial responses. The brain also doesn't average across several trials. And so let me conclude with something speculative, which occurs to me every now and then. What we have here is a network or a system that is able to simultaneously evaluate myriads of nested relations among features of complex cluttered scenes, and do this by having nodes interact that all represent probabilistic values. They have graded responses. And sometimes I think this looks a little bit similar to what quantum computers also try to do, namely evaluate a large number of relations simultaneously using as variables, probabilistic variables. But this is something we can discuss. This is just maybe an unwarranted speculation. This brings me to the end of my talk. Those are the co-workers in my little lab in Frankfurt. Is Katharina Schepkott, Johanna Kloon-Lieb-Kopp, who is very much involved in preparing the monkeys and doing the surgery, but she also helps us with recording. Andrea Lazar, who is at ease with classifiers and computation. Yiling Yang, I told you about the experiments with the sequences. And Liane Klein, who was involved in the attention experiments. In some of the data processing, but I haven't shown much of that, has been done in collaboration with the Orban lab from Budapest. So I thank you very much. And somehow I have to try to get out of the screen sharing.
Thank you very much, Dr. Zinger, for this amazingly clear and inspiring talk. We do have time for a few questions, which have been put in the Ask a Question, under the Ask a Question button, which I will read, and then hopefully you can answer as we go along.
Yeah, I can't see you anymore, but it doesn't matter. If
you can't see me? Oh.
No, it's fine. If you can hear me, it's okay.
Made myself visible, but all right. Anyway, so could you speculate how attention is implemented? Sorry.
Yeah, it's all good now.
Could you speculate how attention is implemented mechanistically?
I can speculate, yeah, but I don't know how it is done exactly. What puzzles us all is that these top-down projections have a huge fan-out, and still they can organize spatial attention and feature-selective attention. I think anatomically it is precluded that they target individual feature-selective nodes, unless there's very, very much heavy learning in the past. But it could be that these representations are less local as we believe. If they are dynamic, then the top-down projection could just influence the attractor dynamics somehow, favoring certain attractors over others. This is something we have to find out.
Thank you. Do you think your finding is about better classification for natural visual stimuli would generalize to the auditory domain, for example, words versus tones?
I would think so. I think this is a general property of cortex because I'm a strong believer that cortex applies the same coding strategies all over the place, functions differently because it gets different input patterns. But I guess one could do the very same analysis in auditory cortex. It would be particularly interesting with language because it's so learned, it's so epigenetically imprinted, and one could easily scramble syllables and make things not understandable anymore, read them backwards, have the same energy, but yeah, see what the classifier does.
I actually think Frederick Tunison, who works on birdsong, has done a lot of this kind of experiments in birdsong auditory cortex. So
yeah.
That point to your answer. Now this is one I'm really interested in. What could be these novel mathematical techniques?
Were I a mathematician, I could probably tell you, but I think it is something that emerges from complexity theory that particle physicists know how to do to solve a large system of nested differential equations that all mutually depend on each other and get simulations done in that way. It's very hard to do these things digitally because they have to be solved serially. And I don't know whether the network interactions in the recurrent network are not, they may not be discretizable. They cannot be discretized. And if that is the case, then anything that resembles more analog computations, simultaneous interactions among a large number of nodes, mutually influencing each other, how to capture this mathematically? I don't know how to do that. I can only ask colleagues who are in that field.
Thank you. How do you think this would play out with ongoing eye movements and saccades every 300 milliseconds?
Well, I think a recurrent network has no problem in first of all, coping with the sequential input that comes with saccadic eye movements, so ever-changing input. But there's an interesting phenomenon that after each saccadic eye movement that is generated produces a corollary discharge in the brain, coming from the brainstem centers that initiate that eye movement, that saccadic eye movement. And that does, for example, erase all inhibitory interaction in the geniculate. So it erases the traces of the preceding stimulus. In visual cortex, it does something similar. It blocks inhibitory interactions, it increases excitability. So it could be that the corollary discharge that is associated with each saccade in the retinotopically organized areas, and it's only there where you see this corollary discharge, which in former times it has been called the pontogeniculate occipital wave or the eye movement potential. It's only seen in retinotopically organized areas where you have a certain interest to erase patterns that have been hanging over from the fixation before, because you don't want to mix up different images. So again, something that needs to be worked out. Eye movements do produce interesting effects in visual cortex, for example. They produce a damped oscillation that is triggered with the onset of the saccade, and then leads to a staggering of the first responses that come in from the retina. But we don't know enough about them.
Okay, so here's our last question from the audience until we have to wrap it up. Do you think similar dynamics could be established on higher levels, such as temporal relations between activations of networks and regions?
Yes, certainly. I'm a strong believer in the conservative nature of evolution. And what we see is adding cortical areas on top of each other. Providing the output of the recurrent network in the upstream area, and feed it into the layer 4 of the downstream area. And then through different recombination, you get different feature selectivities of the nodes, but then they send their stuff up again into the next recurrent network, and they process it again according to the same algorithm. What we tend to see is that the higher you go in the hierarchy, the Of course, the receptor fields get larger. This is feed-forward problem, but also the frequency content, this frequency spectrum changes. The higher areas, they're usually smaller, but they tend to oscillate at lower frequencies, as if they would be able to integrate over longer time spans. Again, something that has been worked out by several people, that if you go up in the brain hierarchy, the power in the oscillations that occur gets more and more distributed to the lower frequencies as you go higher. What that means, again, something one has to explore.
Right. Thank you very much. For all of us, we have another opportunity for a longer discussion with Dr. Zinger at 4 p.m. today. And so if you go to schedule, go to the discussion section for today, you can click on the video stream to open Crowdcast and click on the Ask a Question link. You can post questions ahead of time if you would like. You can also listen to Dr. Zinger's talk again that we have recorded. So I myself have a bunch of questions that I will keep for then, so we have a little bit more time. So I hope to see you all again at 4 p.m. And thank you so much, Dr. Zinger. This was extremely inspiring. We do very similar kind of thoughts in the olfactory system. So this was a very inspiring talk for me. And I think looking at the comments and the clapping for everybody else as well. So thank you very much.
And apologies for the initial complications, but finally resolved them.
It happens, and we're still on time. So we will see you later, 10 p.m. your time, 4 p.m. my time.
Yeah.
Thank you.
Bye-bye. Bye-bye.